Hello, good morning everyone. So today we are going to continue with our presentation where we stopped last time. Very quickly, in general, when we want to define the covariant derivative of any tensor. So like we said, first of all, we differentiate the whole tensor as a whole with respect to the coordinate in that index. So we differentiate the whole tensor with respect to x rho plus. The very first thing we tend to do here is to contract one of the upper indices or contravariant indices. We use mu to do that. The rho follows us as usual, it has to be part of the Christoffel symbol. Then that which we are contracting moves off to the Christoffel symbol just at the same level from the top. And then of course everything else remains the same on the tensor plus. We try again contracting the second tensor on the top of this, the second index on the top of this tensor. And we use mu this time around, and that which we are contracting, which is sigma, moves off to this Christoffel symbol. And again, as usual, rho continues and is attached at the Christoffel symbol. Everything else remains the same. Finally, we try to contract the covariant index, which is lambda, and which is why we have a minus here. So the covariant index lambda moves off and attaches itself together with rho to the Christoffel symbol. But then we use k from top to contract it with down. So this is how we define in general any tensor. We shall see a very more formidable example of this later on. Now what about the covariant derivative of a tensor density? Let's say that this is a tensor density, and by this we mean that this is equal to some g minus w all over 2I if this is some tensor. Of course, w there represents the weight of the tensor. In general, or most cases, you find w to be 1. But just in general, you should know that it could be something other than 1. And so we have g raised to power minus w over 2. Turns out, the covariant derivative of any tensor density doesn't just obey the normal law like that of an ordinary tensor. There is always an additional term to that covariant derivative. So for instance, were this to be an ordinary tensor, that is, this object, T mu semicolon rho. Were this to be an ordinary tensor, what we will expect will be just that. But however, in general, we will always have an additional term to that whole expression. And we are going to see that and why right away. For instance, like we said, if we define it to be this way, then we are going to have this semicolon rho to be minus w here all over 2. Then we are going to have g w all over 2 and then mu semicolon rho. Now I'm going to consider these two objects, of course, individually, and so Leibniz rule applies to their covariant derivative. This is the same thing as g raised to power minus w all over 2, and then I have here with me some g w all over 2 semicolon rho, keeping this term here constant, plus g w all over 2, and then I take the covariant derivative of this. Of course, in this case, what we have next here is this semicolon. This is a scalar. And so this becomes eventually, as it should be for a scalar, the ordinary derivative. This is simply comma rho for that, multiplying this tensor, then plus here gw all over 2, and I have that rho. Now in this case, I could simply just go ahead. Okay, sorry, I have a minus sign here which is missing. I could simply just go ahead with the evaluation. I'm going to have this to give me, let me go gw minus w over 2. Performing this ordinary derivative with respect to x rho, I'm going to have first of all w all over 2 g raised to power w over 2 minus 1. Of course, that's what will be expected because we'll have to differentiate this first with respect to g, plus before multiplying this by the g, the x rho. Then we'll have this attached to it as usual, plus gw here all over 2. This term, of course, is going to give us here what we will expect for an ordinary covariant derivative. This will be the tau mu the X row, and then I'm going to have here with me, since I'm talking about a contravariant index, I'll have the row here. Let me use something here like lambda, which I'll have to contract with this upper index, but then the mu I move over to this, and this is what I get. Okay, so let's have that embedded. Of course, I can multiply out, and so the next thing I'm going to have is W all over 2G raised to power here. With this minus sign, by law of indices, I just have -1, the G, the X row, and then that gives me this multiplying that takes that out, and so what I have left is this, just to put that in bracket, and this is it. And of course, I guess this is already what we are talking about. The term here in the bracket is the same, just as that. And then this one here is exactly this. And so that is what you will get always for any tensor density. Okay, very quickly, let's look at this particular tensor, trying to derive or talk about its covariant derivative. The covariant derivative of this tensor, T mu nu, rho sigma, zeta, alpha, all with respect to beta. Now the very first step, as always, is to differentiate the whole object first. That is this, mu nu, rho sigma, zeta, beta, differentiate the whole thing with respect to x beta. Next, I have a contravariant index, so I'll expect a plus, and I'm going to be contracting with, first of all, the beta will have to follow me, and I'm contracting mu, so let me use lambda. Permit me please, I intend to use the same dummy indices all over, just to avoid having to think of new indices every time. So now, the next thing I'm going to do is to move off what I'm contracting to the Christoffel symbol. It's on top, so I'm moving to the top of the Christoffel symbol. Then I write T. What I was contracting was mu, so I write that here. It therefore means that the lambda replaces what I was contracting. Everything else on that tensor remains the same. And then I have here alpha. Now the next index I have is a covariant index. So this time I get a minus. Again, so what I'll have to contract is that covariant index. So I'm going to use lambda. Beta must have to follow me every time, always. And then what I'm contracting is nu. So I write nu here. And so the tensor is what I have here. Everything else remains the same. Of course, nu becomes lambda, and this is what we get, alpha. The next index I want to contract is an upper index rho plus. So gamma here, of course, so what I'm going to have this time is a plus. I use again, I bring beta along with me, and that is lambda. What I'm contracting is rho. And so I have T here with me, with everything else remaining the same, except of course rho, which I'm contracting. So this is going to be that and alpha. I repeat the same thing for a sigma. Beta again follows me. I use lambda here. This is T. Everything else remains the same. Rho is the same. Of course, lambda here. But then the sigma, which is being contracted, moves here. And then I have zeta and alpha. Now, the last contravariant index that I have there, this again will be plus. Beta follows me. I have a lambda, T again, mu nu, rho sigma, zeta becomes lambda, but zeta again gets moved to this point. I have alpha. Now, this time around minus, because I have a covariant index. This is gamma, which I'll be contracting with an upper index here. So I have my lambda here. Beta, as usual, follows me. And what I'm contracting is alpha. So alpha joins the Christoffel symbol. Everything else remains the same for the tensor, nu, rho, sigma, zeta, except alpha, which becomes lambda. And this expression is a complete expression for the covariant derivative of this tensor with respect to x beta. So this is just to show you or illustrate how the covariant derivative of a tensor occurs for in general. Of course, were this to be a tensor density, then we are going to have an additional term such as this every time whenever you perform a covariant derivative of a tensor density. Okay, moving. Okay, sorry about we had a mistake here. So this alpha here, we had a beta there before. The correction has just been made. So what we actually did was everything else was the same, of course, all along. So the original tensor that we were differentiating should have been the whole tensor without any change, please. Okay, with this, we move very quickly to application of this in something also very interesting. So just as you could have something like the 2, let me say V, the X rho, the X sigma, which is the same thing as V, comma rho, comma sigma, if you like. Well, we could have something also like V sub mu, nu, and then K. So V sub mu, semicolon nu, semicolon K. And of course, this means just operating twice, a covariant derivative, with respect to two coordinates in nu and K. How will this look like? Very quickly, this simply just means, for the first instance, you consider the inner component as some tensor. You could just do like this, momentarily ignoring the mu there, treating this whole thing as a tensor in its own right. In other words, just like what we've explained before, this is the same thing as this, nu, the xk. Then you have, okay, now I'm trying to contract covariant indices, so I'm going to have minus. This is going to be the Christoffel symbol. I'm going to use some lambda here. In this case, what I have contracting the first one is mu, so k follows me and mu is here. So I'm going to have v sub lambda and then nu here. Next, I may decide to contract, of course, that's what I should do. Lambda, the second index here. K always will follow me, nu comes here, v, the first index remains unchanged, but then this becomes lambda. So the usual covariant derivative of a tensor just applies to it exactly the same way. Of course, what it means in essence is that finally we will have to expand these two terms all over again. And then we can obtain a complete expression that is completely in terms of the gamma functions or the Christoffel symbols and ordinary derivatives. We have such a term written as that. We already illustrated that here. So even though we use two different dummy indices, well, we may try to maintain that just to give some flavor to this. Again, the only difference between this one and this one is the interchange between the nu and k. We are still performing the both on double covariant derivative with respect to v sub mu. So what we want to do next is to find the difference between these two. So there are many notations to this. This, by the way, is the same as that. So if you are familiar with quantum mechanics, this is beginning to look like some kind of commutator. Of course, for partial derivatives or the ordinary derivatives, this is always zero. Apparently in GR or tensor analysis, this in general for covariant derivatives is not always zero. Now, but we can see what that gives us. We expect to obtain the Riemann tensor in this form when we perform this operation. For the sake of brevity, I've decided to use this notation to denote this difference, that is this whole thing, to denote this or this, just to help make this easier for me. So that's what we perform next. We are going to move straight forward. This is mu comma k of v sub mu. Now, if what we are really doing is performing the difference between this and this, that is saying this minus this. Now let's look at this immediately. We can see already that these two terms cancel when we perform this difference, because gamma sub nu k and gamma sub k nu are the same. We said is always commutative between the interchange of the two lower indices for a Christoffel symbol. So these two terms here cancel. Now what we are left with will be the v sub mu here, the x. What I have here is k minus. The next thing I'm going to have is the v sub mu k. Now what I have here is the x nu. Of course, since what I'm doing is this minus that, I expect that this will take a positive sign. So I'm going to take gamma rho here, mu, and so what I've got here is V rho K minus exactly, because what we're doing is this minus that. So minus here gamma rho K mu, and then what we have left there is V that. Okay, everything is in order. That's what we have. Now the very simple thing we do next is simply to say d dxk. Now we express this as dv sub k. No, this is dv sub mu. Dx, this is nu. It's going to be minus a Christoffel symbol. So like I said, let me use alpha. I'm trying to use different dummy indices. Using it to contract my mu. So this would be v sub alpha. Always mu will have to follow me. What I was contracting was the mu. So that takes effect there. Now I have minus d dx nu. Now this is what I get. I perform here a differentiation. Right in here, what I'm going to have is dv sub mu dxk minus. This is a Christoffel symbol. I'm trying to contract that, so let me use something like beta, v sub beta. This time a k must follow me. What I'm contracting is the k, so k. Okay, no. What I'm contracting, sorry, is the mu in this case. Yeah, so the mu follows me here. This is exactly what it should be. Okay, now the next term I have there is plus gamma rho nu k. And now what I'm going to have again is dv sub rho dxk. And so what I have there is going to be minus gamma. I'm trying to contract that, so let me use iota. V sub iota. K again follows me, and what I was contracting was the rho. So the rho here is what I have. Now I have minus the Christoffel symbol rho k mu. Now what I have there is V rho. So I have here dv rho dx nu minus Christoffel symbol. I'm again here contracting some nu. So this time around, let me use something like, well, just for the sake of, I want to use n. Nu, of course, will still have to follow me. What I'm contracting is rho, so I'll have v sub n, and that is it. I think that's the last term. Now, very quickly, we can see already that this and this term are the same, except, of course, for their signs. The very first terms, they are the same, so they cancel out. Now, what we're left with for that first one is going to be this. Let's take this one step at a time. Minus. So this ddxk is actually meant to be for both terms here in the bracket. The same thing here. So when I was cancelling the first, I'm just throwing it out to make this easier for me. So this is supposed to be something like this. Alpha nu mu v sub alpha. The sk still. Now, in this case, I'm going to be having minus, right? And that gives us a plus this time around. This is d dx nu. And what I have is this beta k mu v beta. Yeah, that's just about that. And then the next thing we have here, of course, is simply multiplying out. I think there's no harm in simply saying this is plus gamma rho nu k, the v sub rho, the xk, minus here I have gamma rho nu k, gamma iota, k rho, v sub iota. Next, I have there with me minus gamma rho, k mu, and then I have here the v rho, the x nu, plus gamma rho, k mu, and I have gamma here with me, n, nu rho, and so I have v sub n. Yes. Okay, everything seems to be in order. We don't have anything yet that looks okay. Well, so we can move on to the next step, and that will be simply here to say that this very first term here could be written as minus, I think for the sake of argument, we're already done with some of these things here on top, so we can just make everything more elegant. We can clean this. Okay. Now then, we can continue on top. What we have there will be equal to minus. The very first thing we could have there is to differentiate gamma. What we have here is alpha nu mu. Okay, so gamma alpha nu mu, the x k. And I have v sub alpha left all alone this time around. So next, minus, I guess I have to leave this constant by the usual Leibniz rule, the v alpha, the xk. That's what we get from the first term here. Now the next term here does the same thing, plus here we have derivative of gamma, beta k mu, the x nu, v sub beta. Now if that is the case, then we're going to have plus gamma beta k mu, the v beta, the x nu. Okay? Now we can just naively copy in what we had before. The other one there is going to give us, this is gamma rho nu k, multiplied here by dv sub rho, the sk, plus, I'm guessing, okay, sorry, that will be a minus sign, not a plus. So what we had here was this plus this minus gamma rho nu k, and then multiplied here by so we have that gamma rho nu k, then we have gamma iota k rho, and I'm guessing that should be v sub rho, and that is it. Sorry, v sub iota, not rho. This is what we get. The next thing here is minus of gamma rho k mu, the v sub rho, the x nu, and then the very last term there, gamma, this is k mu, I'm guessing, and then the next term there we're supposed to have is n nu rho, and I'm guessing that this is v sub n. Okay, perfect. Now looking at this whole thing, we have here with us some gamma nu k. We're expecting here a term here also in nu k. This is another one here, gamma mu k. We have this, so let's see if something is going to give us. This is k mu. These are dummy indices. The rho and rho are dummy indices. The beta and beta are dummy indices. So as far as we're concerned, these two terms are the same. So actually, these two terms cancel. Hopefully, we should have one more cancellation. And nu k, I guess here I must have had some mistake. The very first one there should be gamma nu mu. Of course, that will be what it is. And then that will be that. What follows that? Then in this one here, which we have, if I followed what we did correctly, this was expanded, giving us two terms. This was supposed to be mu, please. I'm sorry, this whole thing has been messed up. So there was a mistake here. This is supposed to be nu right from this place. This was supposed to be nu. And this second term here is supposed to be. So we can see it already from the last term here already. So we can. Okay, I think a moment, please. So we have missed one of these symbols. It's a confusion. So a new here actually. We had a mu, which we have written as a k. Correcting that and that. What we have now is this is the same with this again, except for the signs. Of course, rho, alpha, alpha, these two are the same. This goes. So please, you can take note of the fact that what we have here should be a mu, and so everything else is in place. Now with this, we can very easily go on to what we're trying to show, and we can clean everything else except the last result, of course, just to see that everything works out well. Now we can write this as the very first term over there, gamma, beta, k mu, the x nu, v sub beta, and then I have here with me minus alpha, nu mu, the xk, v sub alpha. And the last terms we have here will be plus. This is rho, k mu, n nu rho, v sub n, minus, I have here with me, rho nu mu, gamma here, L, k rho, v sub iota. Now, what am I left with? I could decide, I have several dummy indices here. I have beta, doubly repeated in this term. I have alpha doubly repeated here. I have here n. Actually, not just alpha, beta, and all these other ones that I'm calling, but these are all the ones attached to the v's. And also, I have with me over there iota. All these dummy indices, I can decide to change to alpha, if I want to, of course, because it will serve my purpose, so I can do that. And so, if I did that, I could write this as this. What I have there will be alpha, mu, k, dx, nu, v sub, let me just put that all out, means I can do something like that, minus gamma alpha, mu nu, dxk, plus, this is rho, k mu, this again is alpha, nu rho. Next, this will be minus gamma rho. I have here with me nu mu, gamma iota, k rho. Nope, not iota anymore, alpha. All these have been changed to alpha, so I can pull out v sub alpha. And finally, this is all the same as, if I pull out the minus sign and write my v sub alpha all over again, what I have will be this. Oh, let me cut this. This alpha, mu nu, and then I have the xk minus alpha, mu k, the x nu, and here I'm going to have plus rho nu mu, alpha here, k rho minus, this is rho, k mu, alpha nu rho. And this, I guess, should ring a bell. Everything here in the bracket is all we have with our alpha, mu, nu, k. And that's the Riemann tensor. So in essence, we have been able to show that the expression which we started with this, remember what this represented right from the beginning, that the commutator of the covariant derivatives on this particular covariant vector ends up giving us minus v sub alpha, the Riemann tensor. This is mu nu k. Ends up giving us that, which was what we intended to show right from the beginning. As time goes on in this series, hopefully we shall be looking next at the properties, some of the symmetry properties of the Riemann tensor. and its applications, and also maybe the Christoffel symbol. With this, thank you all so much for watching.